Okay, so let's look at what happens when we transform and combine these variables. We've done this before. If you remember a few chapters ago, we talked about how when we add or subtract a constant or when we multiply or divide by a constant. So this is going to be very similar to that. So in this case, let's look at, here's your data that's given to you. Given to you already. It says copy the data from yesterday's lesson below. So here's some sample data there given to you for the various probabilities here. So these x values here represent potential wage values. And so these were not evenly distributed and they were randomly assigned. And so these would be the probability of getting a wage that's $1, $5, $7, $10, $15, $25. Calculating the mean wages for this comes from, remember this formula right here, because they don't all have the exact same probability, right? I have to multiply 1 times 0.227, add that to 5 times 0.091, add that to 7 times 0.455, all the way through. So I get a mean of about 7.5, and then I get a standard deviation of about 6.24. If you remember, your standard deviation is your square root of your variance. So subtracting your data point from the mean, so 1 minus 7.5, square that times the probability of that happening, so times 0.227. Do that for every x value there, and then take the square root. Add them up and then take the square root. And so we get a standard deviation of about 6.24. So now let's look at what will happen if we manipulate this data. So to make a decision about what raise should be given, so if you read the beginning there, the boss here is trying to decide what kind of raise she wants to give them. If she should give everyone a $10 per hour wage raise, so add $10 to everybody's wage or double everyone's wage. So we're going to complete a couple tables here to help us decide how we're going to what she's going to do about that. So we're going to add $10 per hour for each one of per hour for all employees. So that would make this person would then earn $11. This person would earn $15, $17, $20, $25, and $35. My probabilities here now, they're going to stay exactly the same. Okay, I didn't change how often somebody was earning $11 or how often somebody was earning $15 or how often they were earning the $17. So my probabilities here stay exactly the same. So if I go through and I use my formula here to calculate, here we go, and I use this formula here to calculate my mean here, I'm going to get a mean value that is going to be my mean plus 10. Remember when we talked about this before, basically all we've done is we've taken the various data points along the number line here and we've just shifted them over 10 places. So my mean is still going to be located in the same spot within the data set. It's just going to be a value of $10 higher this time. So in this case, our mean would be 17.5. Okay, and if you don't believe me, go through and do the actual math. 11 times 0.227 plus 0.091 times 15 plus 0.455 times 17 plus 0.136 plus 20 plus 0 plus 0.091 times 35. And that should give you the 17.5. As for my standard deviation here, remember standard deviation is a measure of spread. And even though I took my points and I shifted them up the number line by 10, I did not change how far apart those points are. Those points stayed in the same basic shape and cluster. So my spread isn't going to change. So when I add a constant here, my mean will shift by the constant, but the spread will stay the same. So now let's look at what happens if I double the wage of the employees. So this time I'm going to double everybody's wage. So this person here that was earning $1 now earns $2. This one earns $10, $14, $20, $30, and $50. Hopefully just by looking at this, you can see, and you remember too, from when we did this before, that this is going to change the location of in addition to shifting my dots on the number line, I'm also going to change the shape of those dots. They are going to be moved down, and their spread is going to change. They're not going to have the same exact, cluster as to where I'm not taking the entire cluster and just picking it up and moving it down. I am shifting the shape of that cluster as well. So this time, my mean is going to change just like it did before. And this time, my mean will double. So before, because that's what I did to with my constant, right? I multiplied it by 2. Before, my mean went up by the 10. So I added my constant to it, and my standard deviation stayed the same. This time, my mean will double because that's my constant that I did, right? I multiplied everything 2 times. Okay, and my standard deviation will also be multiplied by 2. So in this case, my mean, which was 7.5, my mean is now going to be, 15? 15. And my standard deviation, which was my 6.24, is now going to be 12.48. And again, you can plug this into your calculator to find standard deviation, right? I could put in all my wages. I could put in all the wage values here in one list, and then all the probabilities, which those are still the same. I can put all the probabilities into the list next to it, and then I can one-var stats it for those 2 lists, and it will give me both my mean and my standard deviation. Well, it will give you your mean. It'll give you your standard deviation is what you really want there. And so now, when you're multiplying by a constant, that's going to affect both. It will affect the mean and the standard deviation. In this case, they were both multiplied by the particular, by the constant. So this third question here, which option would you prefer? Well, I think that depends. It depends on maybe which wage value I had to begin with. As a worker, I'm going to want them all doubled. But as the employer, you need to kind of look at it. I've got a smaller average value down here when I double everybody's values. However, my spread is much bigger. So I've got some people that are making a lot of money and some people that are making very little money. So it has a big spread within those salaries, where above, even though my mean is slightly higher, I don't have people that are making this, kind of extreme amount of money. So let's kind of summarize and look at some of our big ideas here. So I'm going to split this in half here so if we add or subtract by a constant, what are the things that happen, right? Well, the shape stays the same. Shape is the same. That won't change. The center will change, though. The center will change by the constant. So whatever I added or subtracted to it. And my spread, or my variability, so that variety within the data, that spread within the data, that is also going to stay the same. So if I divide or multiply by a constant, this time now, again, my overall shape stays the same. It might be more spread out, but the overall shape, or more, if it's a curve, it might be a wider, flatter curve. It might be a skinnier curve, but the shape is still the same, that curve. Okay, the center is affected by the constant. So the center, it will also change by the constant. And this time, my variability, my variety within that data, it's going to change by the constant as well. So the variability changes by the constant also. So let's look at one more example of this real quick. So a large auto dealership keeps track of sales made during each hour of the day. Let X equal the number of cars sold during the first hour of business on a randomly selected Friday. Based on previous records, the probability distribution of X is as follows. 0 cars, 1 cars, 2 cars, 3 cars, and the probability for those. The random variable X has mean 1.1 and standard deviation of 0.943. Remember, we can write the mean as not as a whole number. Suppose the dealership's manager receives a $500 bonus from the company for each car sold. Let Y equal the bonus received from car sales during the first hour on a randomly selected Friday. Sketch a graph of the probability distribution of X and a separate graph of the probability distribution of Y. How do these shapes compare? Okay, well, let's look at what we're graphing here, right? So the probability of X is cars sold. This is not going to fit. So we've got 0, 1, 2, 3. This is cars sold. And my probabilities here, my highest one is 0.4. So let's go 0.1, 0.2, 0.3, 0.4. And so 0 is a 0.3. 1 car is a 0.4. 2 cars is a 0.2. And 3 cars is a 0.1. Okay, so that's a graph of the cars sold of X. And so it also asks to draw a separate graph of the probability distribution of Y. Well, my probability distribution of Y, so this is the money he's going to earn in the bonuses, right? This is my probability. He earns a $500 bonus from the company for each car sold. So basically, we're adding $500 to him for each car that is sold. So he could earn 0 money if no cars were sold, right? He could earn, let me move the money sign down there. He could earn $500 if 1 car was sold. He could earn $1,000 if 2 cars were sold, and he could earn $1,500 if 3 cars were sold. My probabilities here, 1, 2, 3, 4, my probabilities here are the same, right? Because his bonus is strictly tied to the cars that are sold. So my probabilities here are the same. My graph basically should look exactly the same, just the values on my x-axis were changing. So I'm asked to find the mean of Y. Well, I know the mean of X, which is 1.1, so I can just take 1.1 and multiply that by 500, which will give me 550. And then it asks us to calculate and interpret the standard deviation of Y. Well, since in this case we were multiplying by a constant here, we're going to go ahead and that's going to affect my standard deviation. So I'll go ahead and multiply the standard deviation, which is given to us up here, the 0.943. Multiply that by the 1.1. Okay, I don't know if y'all are going to have a weird audio glitch right there. So just to be sure we're all on the same page, we are calculating and interpreting the standard deviation of Y. So 0.943, and I'm going to multiply this by the 550 because that's my constant, which is going to give me 471, whoops, I forgot the one. 0.70, but I'm not done, right? It asked me to interpret standard deviation. So remember, when we interpret, we have to put in our context. So the bonuses, because that's my context, that's the bonus that he gets, right? The bonuses typically vary by $471.70 from the mean of $550. So we put our context in there, we define the standard deviation, and we define the mean. So again, I don't have room to write it there. The bonuses typically vary by $471.70 from the mean of $550. So looking at number 4 here, the manager spends $75 to provide coffee and donuts to prospective customers each morning. So the manager's net profit during the first hour on a randomly selected Friday is $75 less than the bonus earned. Describe the shape, center, and variability of the probability distribution of T. Okay, so in this case now, what are we doing? Well, in this case, we are subtracting by a constant, right, because it is $75 less. So my shape, regardless of what I do, my shape stays the same. In this case, I'm subtracting by a constant, so my center, which is my mean, is going to go down by $75. So my mean now is $475. And then because I'm subtracting by a constant, my standard deviation does not change. My variability or my spread stays the same at that $471.70. Okay, so let's look at what we have going on here. So we have this same employer who is apparently now randomly assigning her employee wages. Don't work for anybody that ever does that to you. And it says, additionally, at the end of each year, she gives her employees an hourly raise. The bonuses are assigned randomly according to the probability distribution Y, given below. Assume that X and Y are independent. So looking at number 1 here, we're asked to find the mean, variance, and standard deviation of the probability distribution of X. Remember, our mean of this is going to be found by calculating it like using that formula. So we get 11.85. Our variance is going to be the sum of the data point minus the mean times the probability squared times the probability, which gives us 4.93. And then the square root of that is our standard deviation at 2.22. Again, hopefully you're doing those things on your calculator. So they're asking to do the same thing for the probability distribution of Y for that annual raise there. So we've got a mean of 1.6, a variance of 0.839, and a standard deviation of 0.917. Okay, please take a second. Put those into your calculator. Make sure you're getting those same answers. Nobody is going to do this for you on a quiz, on a test, on your AP test. So you need to know where these came from. Put the Y values in a list, put the probabilities in a list, do your 1-bar stats, make sure you're getting the same numbers. So they give us a formula. N equals the new hourly wage for the upcoming year, which is just going to be X plus Y. So what are the new possible wages for the year? Well, we have 10. Somebody could be earning $9 and get the $1 bonus. 12, they could be earning $9 and get the $3 bonus. Let's see, 13, they could be earning $12 and get the $1 bonus. 15, if they're earning $12 and get the $3 bonus. And then 16, again, earning $15 and getting the $1 bonus, or 18 for earning $15 and getting the $3 bonus. So what is the probability of an employee being assigned a $9 wage and a $1 raise? Show your work. Well, what we're looking for here is we're looking for the probability that they're earning $9 and they got the $1 raise. So I want these two things to happen at the same time. Remember at the very beginning, it told us that we were to assume that these things were independent. Okay, so basically what we're looking for here then is the probability of 9 times the probability of getting that $1 raise, which is 0.3 times 0.7, which gives me 0.21. Complete the table below for the probability distribution of n equals x plus 1 and find the mean and standard deviation. Well, my probability of earning $10, which is this right here, right, because 9 plus 1, right, is 0.21. My probability of earning the $12, so $9, earning $9 and getting the $3 bonus, so that would be 0.3 times 0.3, or 0.09. my probability of earning $13, so earning $12 times the 0.7 probability of earning the $1 bonus is 0.315. Okay, and now I'm going to tell you to pause for a second, do the last three on your own, and then turn it back on and check your work. So this is what you should have gotten. For the $15, it's 0.135, 16.175, and 18.075. When we calculate our mean of this, multiplying all the probabilities times the values and adding them together, we get 13.45. Our variance is 5.76, and our standard deviation is 2.40. Again, if you cannot do these, you're kind of dead in the water. You need to make sure you can do these, and if you can't, you need to ask. Okay, so looking at number 4 then, if n equals x plus y, complete the following in terms of x and y. So the mean of n and the standard deviation. So let's look at what we've got here, right? Our mean of y was 1.6. And our mean of x was 11.85. When I add those two things together, I get 13.45. So the mean of n, which remember n is found x plus y, is the mean of x plus the mean of y. The standard deviation of n is the square root of the standard deviation of x squared plus the standard deviation of y squared. Okay, so let's look at what that would be, right? Our standard deviation of x is 2.22, so 2.22 squared plus the standard deviation of y, which is 0.917 squared. Apparently I ran out of room. And I need the square root of all of that. And when I calculate that out, I get the standard deviation here of n, this 2.40. So let's recap our big ideas here, right? If we're adding and subtracting random variables, so like we did before where we added x and y, or if we subtracted x and y, then the mean is just going to be the two means added up. The mean of x plus y or x minus y is the mean of x plus the mean of y. And my standard deviation, when I add them up, is just going to be the square root of the standard deviation of x squared plus the standard deviation of y squared. And when I subtract them, it is also, I'm going to subtract my means. So my mean of x minus y is the mean of x minus the mean of y. That's my new mean. And my standard deviation, when I subtract that, is still going to be the same. I'm still going to add those two standard deviations squared. I'm going to square the two standard deviations, and I'm going to take the square root of that. That is still going to be my standard deviation, even though I am subtracting there. Okay, so let's go back to this car dealership. So back at this car dealership with the boss that gets the $500 bonus for every car that's sold. So define t, which equals x plus y. Assume that x and y are independent. So it wants you to find and interpret the mean of t. Well, my mean of, I hate that. My mean of t is going to be, right, the mean of x plus the mean of y. My mean of x is 1.1. It helps if I put the decimal point in the right spot. My mean of x is 1.1. My mean of y is 0.7. Therefore, my mean of t is 1.8. And then it asked me to interpret it. Okay, So when I'm interpreting it, I need to state, because it's an average, I need to state that I'm going to do this lots and lots of times. So over many, many Fridays, put it in context. Over many, many Fridays, the dealer expects to sell, on average, about 1.8 cars. It's sell and lease. Y is leasing, X is selling. So put all that context in there. So over many, many Fridays, the dealer expects to sell and lease, on average, about 1.8 cars. So then it asks us to calculate and interpret T, the standard deviation for T. Well, my standard deviation for T, remember, is going to be the standard deviation of X squared plus the standard deviation of Y squared, and we'll take the square root of that, which is going to give us square root of 0.943 squared plus 0.64 squared, which gives us 1.14. And I'm not done because I have to interpret that. And so if I'm going to interpret that, I'm going to say that the number of cars leased and sold typically varies by 1.14 from the mean of 1.8. Okay, so again, I'll use my context. The number of cars leased and sold in the first hour on Fridays is going to typically vary from the mean of 1.8 by about 1.14. Okay, and then looking down at number 3, the dealership manager receives a $500 bonus for each car sold and a $300 bonus for each car leased. Find the mean and standard deviation of the manager's total bonus for B. So B is going to be B will be the bonus for cars sold plus the bonus for cars that are leased. So my mean of B is going to be my mean bonus of the cars sold, which is 500 times 1.1, right, plus the mean bonus, which is 300 times 0.7, right? 1.1 is my mean cars sold, 0.7 is my mean cars leased, which gives us 760. My standard deviation for B is going to be 500, because I'm multiplying, right? And that affects my standard deviation. So 500 times 9.43 squared, that's my standard deviation for his bonus for cars that are sold. And then my standard deviation for his bonus for cars that are leased, he gets 300 per car. And so that affects my standard deviation. So 300 times 0.64 squared. Okay, and then I add those together and I take the square root of those and I get $509.09. So over many, 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 many Fridays, the manager expects to get an average bonus of $760. And then the average bonus of the manager, based off of cars leased and sold during the first hour on Fridays, differs from the mean of 760 by about $509.09. Okay, so we'll be practicing a lot with this in class.